These are the Lesson 8.2 notes, Properties of Exponential Functions. Today we're going to be graphing transformations of exponential functions. We're also going to work with continuous compounding as well. The first thing we're going to do is we're going to graph this exponential function y equals 3 times 2 to the x power. I'm going to use the standard viewing window on my calculator using -10 and 10s as my x mins and x maxes, y mins and y maxes. I'm going to type my equation under the y equals menu. We're going to graph it on your calculator so you can get an idea of what it looks like. And for specific points, you can use the table feature, second graph, and find some specific values your graph goes through. Namely, I'm going to plot values like 0, 3, 1, 6. You'll notice that 212 would be off the screen, so I'll plot some negative values as well. -1, 1.5, and -2, 0.75. This graph is going to kind of hug this x-axis, and eventually it's going to come up through these values and then move upward forever and ever and ever in this direction. It will continue to move to the left in this direction, but it will never cross the x-axis. Now in our equation, the role of the 3 is the y-coordinate when the graph crosses the y-axis. It's the y-intercept. It's also known as the initial value. The role of the 2 comes from the idea that as you move from left to right, the y-coordinates are doubling as you move from left to right. Every time you move one unit in the x direction, the y-coordinate is going to double. This is known as your growth factor. And you'll notice if you look at the numbers on the calculator over here, each time we move one value in the x direction, the y values get doubled. The horizontal asymptote is not something we've talked about recently. The horizontal asymptote is the line that this graph gets really close to but never quite touches. That's this x-axis right here. If you can imagine this line right here that we're working with, our graph never touches the x-axis, but it gets really close to it as you move from left to right. So we say the horizontal asymptote is the x-axis. As an equation, we say that's equal to y equals 0. As we look at our next few graphs, you'll notice that each of these graphs features a 3 and a 2 in it, similar to our original parent function, but there's going to be a little bit of a difference between each of these graphs and the original function. Using your graphing calculator, I'd like you to plot the graphs for these three functions down here. And then what I'd like you to do is see if you can figure out what transformation has taken place, what change has taken place compared to the original graph, and then where is the asymptote of your new function at. It may still be the x-axis, but it might move. So take a few minutes, pause the video, graph these functions, answer the questions, and we'll come back and see what your work looks like in just a little bit. The first graph is the equation y equals -3 times 2 to the x power. The -3 is your initial value, it's the y-intercept, and if you compare this versus the original graph, you'll notice 0, 3 is now 0, -3, 1, 6 is now 1, -6. Our graph has reflected over the x-axis, and that's the transformation that's taken place. You will also notice that the asymptote is located in the same spot that it was for the original parent function, which is again still the x-axis. For the second graph, this graph goes through points 0, 4 and 1, 7. Compared to the original graph, which went through 0, 3 and 1, 6, the y-coordinate has moved up 1 unit. In fact, this entire graph has moved up 1 unit, and that's the transformation that's taken place here. Up 1. This is called a translation. The asymptote has also been moved up 1 space. This graph gets closer and closer to this vertical line, which is at y equals 1. That's what we say the asymptote is. This line crosses the y-axis at 1, so it's the equation y equals 1. On our third graph, we have points like 0, 6 and -1, 3. Our original graph had points at 1, 6, 0, 3, so this graph has been shifted left 1 unit. The point that was at 1 is now at 0. The point that was at 0 is now at -1. Our graph has been moved left 1, so this is a translation left 1. The asymptote for this graph is the same as it was for the original parent function. It is still the x-axis. So to recap, if you have a negative number on the outside, this is basically reflecting your graph over the x-axis. If you have a plus 1 on the outside, this is going to deal with a vertical shift. Plus is going to be in the positive direction or up. A minus would be in the negative direction or down. If there's a plus or minus that's grouped with the x in the exponent, this is going to be a horizontal shift in the opposite direction of what you think. So x plus 1 is going to move your graph left 1 unit. If it was x minus 1, it would move it to the right. See if you can write a function for the graph with parent function y equals 3 times 2 to the x power, translated left 2 units and down 8 units. Pause the video, see what you come up with. We'll see if your answer is right in just a minute. So here's your equation. Notice if we're moving to the left 2, we group our exponent with this x plus 2. So a left translation, you're going to have x plus something. 8 units down means on the outside you're going to write minus 8, and there's your function. The parent function at the right on this graph is in the form y equals a times b to the x. I think you could come up with the equation for this parent function. See if you can do that, and then take that equation or that function and see if you could come up with a translation for that function that would move your graph right 3 and down 2. First step, give me an equation for this graph right here. That's the parent function. Then write the translation. Pause the video. We'll see if you get the right values in just a minute. So the equation of the parent function is y equals negative 4 times 1.5 to the x power. Your a value is negative 4. That's your initial value. It's your y-intercept. Where does the 1.5 come from? Well, the next value on your graph is at negative 6. So if you take negative 6 and divide it by the previous value, negative 4, you get 1.5. That's your growth factor. And then you have an x for your exponent. To check it on your calculator, I typed in the equation. I graphed it. It matches my graph. To move your graph right 3 and down 2 units, we're going to start with our same parent function, y equals negative 4 parentheses 1.5. To move it right 3 units, we're going to go x minus 3 in the exponent. To move it down 2 units, we're going to do minus 2 down here. If you want to check it on your calculator, that's fine. Just make sure when you type this into your calculator, not only are you going to put the 1.5 in parentheses, but you're also going to put the exponent, x minus 3 in parentheses as well. This will ensure that your graph will move horizontally the correct direction you want it to move. When I apply the minus 2, you'll see compared to the original graph a slight change. It should be moved right 3 and down 2. The last thing we're going to look at today is solving problems involving continuous compounding. Now, I have my money in a credit union, and what that means is that if I put, let's say, $1,000 in a bank account or a credit union account, the bank or credit union will reward me for trusting them with my money, and they give me a small token of appreciation, which is a percentage of the amount of money I put in the bank or credit union. Now, what will happen is if I have $1,000, maybe the bank will give me $5. So now I have $1,005. Now that I have $1,005, the next payment I get of interest might be $5.10. So I'll get additional money that accumulates. So the interest is adding money to my bank account. The next time I earn interest, it's going to be a percentage of that bigger amount. So every time I get interest, it's going to be a little bit more each time. Now, most banks and credit unions offer interest payments quarterly, 4 times a year, maybe it's monthly, 12 times a year. Continuously means you're earning interest basically every second, but the interest is so small that you aren't going to notice this accumulation occurring very quickly. The formula that we use for continuous compounding is sometimes called the Pert Formula. I just want to explain what the variables in this formula stand for. The A in this formula stands for amount. Is the amount of money that you end up with in the account after T years. The T in the formula actually stands for years, time in years. The P in the formula stands for the principal amount. This is a principal. The principal amount is basically your initial value or your starting value. This makes sense because when we do exponential equations, it's kind of in the same position that our little a is usually in. E is a mathematical number that's approximately 2.7. We'll talk about that shortly. R is your interest rate. The interest rate is written as a decimal, so if the interest rate is 5%, you would use 0.05. So let's look at this question, investing $1,000 in an account at a 1.8% interest rate for 2 years. Let's assume continuous compounding. We're going to use the formula A equals PE to the RT power. And in this case, the initial amount that we're starting off with is $1,000. That's our P value. Lowercase e is about 2.7. We just leave it like this. Our interest rate is 0.018. 2 years is our time period. To figure out what this amount of money we're going to end up with is, we're going to use our calculator. There is an e function on your calculator. You can find it in a few places. One place you can find it is by doing second and then this ln button, which we'll be talking about later on. And then in your exponent, we're going to do the product of 0.018 times 2, where you put that in parentheses, we hit enter, and you get this amount of money. It makes sense to round amounts of money to the nearest cent, so we're going to call this $1,036.66 because the 5 is going to round up to the next decimal place. So after 2 years, we've earned about $36.66 in interest. Great. Now, how much should we end up putting in an account that earns 1.8% interest for 2 years if we want to end up with $2,000? Well, here's a case where my amount after 2 years needs to be $2,000. That's my A value this time. I don't know how much money I'm going to start with, but I'm using the same interest rate and time as I did last time. What we want to do is we want to solve this equation for P. So the easy thing to do here is just divide out everything that P is being multiplied by, which is e to the 0.018 times 2 power. We're going to divide both sides by that, which means on the right side of the equation, this stuff's going to cancel out, and we're just going to be left with P. On the left side, we're going to crunch out 2,000 divided by e, which is second, and then this ln button, to the 0.018 times 2 power. And the answer we get is $1,929.28, and that is what your principal amount would need to be. So if you wanted to end up with $2,000 after 2 years, you'd have to start with this amount of money in the bank.